it's like assignment 3 on here, and I went and tried to do it, and I couldn't do it. So I was like, okay, I'm in trouble.
Okay, is there an assignment on here? Oh, there is.
Yeah.
Oh, these are examples.
Yeah, there's like some examples, and then it says like it's like assignment 3, assignment 4. But I don't know if any of this is ever due or what, but at least it's
Okay, well, let's just jump right to the assignments. Those are sort of more interesting to do. All right, I'm gonna skip number 1. It looks kind of long for it. We might get detracted from it. So start with number 2 here if you see my screen.
okay. Yeah, sorry. And number 1, I know. Sorry, and I do
Okay.
know number 1. Like he went over the coin tosses and how like you you put 2 and then it could like to the power of how many tosses you do and all that. So I do kind of understand that.
Yeah. Well, let me just give you a little more information on this one. So I like to draw the sample space, and you have to sort of pattern this out. So and there is a pattern here. It's heads, 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 tails. So you just change one at a time. Heads, tails, heads, heads, tails, tails. Okay, and then you flip back to tails, tails, tails. All right, I guess I misspoke. I'd change more than one at a time, but then you keep going. You got tails, tails, heads, tails, heads, tails, tails, heads, heads. And there's tons of ways you can do this, but you got to get the sample space. And it's like you said, it's 2 to the 3rd, which is 8. This is the probability of getting at least one head. So if you have the sample space, which there's lots of problems I can ask you to do. You would then just sort of circle the ones that okay, that one's right. So at least one head, 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 one head. So there's actually 7 out of 8 that have one head. But there's lots of questions I can ask. Like there's many different ones that it could be. So knowing the sample space is sort of key. And we'll look at question 3 next. I don't know if you're a card player or not. If you haven't looked at a deck of cards in a while, it's good to have. Just go to Wikipedia also and get a picture or just Google search, because you really that is your sample space. Is seeing all the cards. Let me see if I can grab one right here to help us with this question. So when you have your sample space, and what I mean by that those are the sample space are the possible outcomes. Okay, so like there's 52 outcomes here, and the probability of the thing you want, whatever you want here, it's the number that work over the total. So with a deck of card, your total is 52. In the previous example, it was 8 because there are eight possible outcomes. It's always the possible outcomes or the total outcomes are on the bottom. And then it's what do we want here? Well, we want a face card or a diamond. So we want all of these. That's why sometimes it's good to look at a deck picture or a diamond. And so then you want these. Now you do not overlap. You don't double count. So you could sit there and count with 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of those. Plus there are 3, 3, 3, 3, 12. So there's 22 out of 52 that satisfy this. You seen this before?
Yeah, like so this is sorry, I was getting rid of something that popped up on my screen, but can we go right back over the 22 part?
Yeah. So you're literally counting the ones that work. Okay. So what works? Well, it has to be a face card. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards.
Okay.
Plus there's all the other diamonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 other diamonds. But you don't double count. Like you don't count the ones that are both.
Okay, I see. Okay, so because you already had those 3, like
yes.
You can't see where I'm pointing, but the final 3 in that diamond row.
Yes.
Okay, I see what you're saying. Because there's, how many is there normally? I don't play cards ever. It's 13 per.
Yeah, let me copy this down so you get some numbers that you might see. So there are 13, 13, 13, and 13. 13 of each suit is what they're called. Okay. And then color, okay, it's red and black, so they're divided in half by color.
Okay.
Okay, and then the rest is kind of just weird. There's not really a nice division here, but these are the face cards. And
yeah, there's 3 per, right. So there's 12
Yes.
total face cards. Okay.
Yeah.
And that's how you did that. Okay.
Yes. And again, having the sample space really, and that this is the sample space, like all the possibilities, that really helps to be able to answer these questions.
Yeah, no, I was trying to figure this problem out specifically with my mom because I was so confused. I was like, what am I even looking at? And like her trying to explain it, I think she's much smarter than me. So she was getting it. And then like I was like, I don't get it at all. Like I don't. But this visualization helps a lot.
Okay, now I want to do something real quick here. So this one says the word or, and we're gonna just change one word, and that's that's the challenge here in this class is one word can make all the difference. So let's say it's a face card and a diamond this time. Okay, and a diamond. So the probability of this thing that you want, which is face card and diamond, it's still over 52 because that's your sample space. But how many work? How many are both a face card and a diamond? Okay, well, it's just these three this time because it has to be both.
Yeah.
Both. So I don't know if that's easy to see. So there's just three. So one word changes the answer significantly. So there's this language in or means one or the other or both, and means both. And these are the words you're going to see in this class. We actually see it in the next problem.
So or can actually mean both.
Well, it's you don't double count, but let's go back up to this one we did where it said or. Both is good. See how the overlap is here?
Yeah.
Okay. Let me actually bring this down. So to try to explain this again. So if we let me just circle. Actually, that's a bad color to use. Let's use this color. So here are all of the face cards, and here are all of the diamonds. Okay. So the both is the overlap. That's the both.
Okay.
So it's analogous to this. So sometimes you hear this in classrooms. Or people very logically centered will say things like, let me actually type this because I think this will help. They will say something like, do you like football or basketball? Okay, and the answer, let me get this, let me just make this a little bigger here. The answer is, they will answer it this way. Why can't I get my spell check? They will answer it this way. They will say yes. And here's what yes means. Yes means both.
Okay.
Yeah, I like them both. Okay. But you want them to choose. Normally we want someone to choose, but in probability, it could be both. You don't have to pick one or the other.
Okay.
Okay, so it's that. So let's you will get in a traditional probability and statistics class, you will get some card problem on an exam at some point, but it's not the whole exam, so we don't spend all our time on that. So a businessman has two secretaries. So the probability that the first one is absent on any given day is 0.08. The probability that the second one is absent on any given day is 0.07. Probability that both are absent on a given day is 0.02. So whenever you have two events like this, you're generally asked to draw what's called a Venn diagram. Have you seen that in class?
Yeah.
Okay. So this one's a little odd because usually it's like probably that you like math or probably that you like English. Here it's kind of negative, absent. So like number one absent, and who has two secretaries? It's weird. Okay. So you actually start with the both. The both is the and. This middle region represents and. So you put that in there. That both number goes right there. Now, the first one is absent. Like I'm going to write the value of X right there. X plus 0.02 has to equal to 0.08.
Okay.
See that?
Yeah.
Like the whole circle has to be 0.08. So that means that X is 0.06. So we replace it, 0.06. Now we're going to put a Y here. And for this other one, Y plus 0.02, because that's the middle one, has to equal 0.07. So that means Y is 0.05. Okay, now what is implied in this Venn diagram, but not stated, is that there's also the probability that neither of them are absent. And that's the number that's out here. I don't know if you covered that in class, but the whole thing has to add up to 1. So 0.06 plus 0.02 plus 0.05 plus z has to equal 1. And that, that number is pretty high here. Let's see, that number is whatever. So 0.08, 0.13. So 0.87 is the probability that they are, neither of them are absent.
Okay.
Okay. Now, why do we draw the Venn diagram? Because there's actually quite a few questions that could be asked, and all the questions that are asked are either some combination of like circles or the rectangle or like just parts of one or the other, and that's why we ask it. So part A says, what is the probability that the first or the second one or both, see how that or both will be absent? So in a Venn diagram, the or is the overlap of the two circles and that middle circle. That's what or is. So that means you have to add up those three numbers. Because it could be first one's absent or the second one's absent or they're both absent.
Okay.
And if see how that number 0.13, if you were to just add up 0.08 and 0.07, you're double counting. You're double counting the middle part.
Okay. I get what you're saying.
And that's why you don't double count it. There is this thing called there is a formula for this where you can just do it without drawing the Venn diagram, but I think it's very helpful to see it visually.
Yeah, it is.
Okay.
And hopefully I'll remember the Z thing, because that's helpful too.
Yes, and that sometimes is a question that's asked. There's I don't know, there's schools that they always ask that question on their exams. So what is the probability that only one secretary will be absent on a given day? So this one means that the first one could be absent or the other one could be absent, but not both. So only one means it's either the first one was absent, the second one is absent, but not both. So it's the point, what do we say here? 0.06. And this is the 0.05. You add them together, 0.11.
Okay.
A couple of things about probabilities that we should talk about right now. The first is that probabilities go from 0 to 1, and I use this word inclusive, but I'll show you another way. It's 0, 1 with brackets. That means it could be 0, could be 1. Here's what it can't be. Never negative. So if you get a negative number, you have done something wrong. Okay, or greater than 1. That's the other one. Okay, which means you should just redo it, or don't like it's a really bad thing to do. Like, to say, it's greater than 1.
Okay.
So and sometimes that happens. You do something, or you don't really remember how to do it, and then you get a number, and you just think, oh, I'll just but that's really bad. Really bad. Okay. Any questions on Venn diagrams before we move on?
No, that was good.
Okay. So the next problem is a frequency table and a joint probability table. Let me snip this in. All right, so there's actually a relationship between these. All right, so the relationship is the frequencies are like the counts. It's like you went out, you went to your favorite intersection, and you watched. Well, actually, there's not many accidents, but they're literally counting. They're saying, okay, 20 males had an accident, 40 females had an accident, and so on. All right. The probability, this isn't a probability. 20 is not a probability because it's greater than 1. So the joint probability, you take each value in each cell and divide it by the supertotal. I call it the supertotal because it's the total of the totals, because there's both a row total and then there's a column total. You want the supertotal. Sometimes on an exam, you will only be given, this is, you know, depends on the instructor. Sometimes you're only given the data, you're not given the totals. And so you have to add that row and column total to your thing. But in terms of like, what do you do here? So for the first one, it's 20 over 200, but it's 0.1. Female is 40 over 200, which is 0.2. And then the total, it's 60 over 100, but you could also add up these. It's 0.3. I guess I should probably specify why that is. So you can either add it up. So it's either 0.1 plus 0.2 equals that, or it's 60 over 100, either one. And then you do the same thing for the other ones. 80 over 200, sorry, 200, not 100, 80 over 200, 60 over 200. That's how you get these cells. So it's 80 over 200, which is 0.4, 60 over 200, which is 0.3. And then you can add them up, or this. So this is 0.5, this is 0.5, and then this is 1.
All right, that makes sense.
Now, this is not quite how, I'm gonna just redraw the joint probability table.
Okay.
And then so actually, let me do it the other way. Sorry. Let me grab the frequency table. So the more common question, the more, you know, quiz test question is to say, what is the probability that a male driver has an accident? Now it's over 200 because that's the super total. It's always over the super total. But which cell are we looking for? Male and has an accident. And you can, when it says male has an accident, you can think of that as an and. So and refers to one cell in the table. It's this one right there.
Mm-hmm.
So that's 20 over 200. It's 0.1. It's the same that we said before. Now I could also ask you for something like this, the probability that it's female or no accidents. Female or no accidents. So I'm gonna color code this one because it's easy to do. So there's two possibilities. You could either have no accidents, or you could be a female. And do you see how there's an overlap there?
Yeah.
Okay. The or means that you're gonna have a problem, or you don't want to double count. So see, if I just went female, female is 40 plus 60. 40 plus 60 or 100, you guys put that. But you usually just go by the cell totals. And then the no accidents is 80 plus 60. Do you see how I've double counted the 60?
Yeah.
You don't want to do that. So you remove one of them. So sometimes it's better just to circle the ones that work.
Okay.
And you just add those up over, well, it's over 200 again, because that's the total. And that's the more realistic question you're gonna get. That ends up being 0.9. That's the more common test question.
Okay.
There.
Yeah, no, that's one of the things I know. Just like it's tough. Like I don't have a good brain for like seeing simple examples and then like translating that to like the complex stuff. It's tough to see that like in the simple stuff, like when he went from like here's how you do cards, and then like here's like a super complex one in my brain that can do it.
These are just standard problems, though, test questions. I mean, hopefully you're not going to get anything more sophisticated than this.
Well, like the second one you gave me, just like it might have been harder to figure that one out. I could have made a mistake compared to like maybe the table that he did was a little easier.
Yes. So visual is always good here. So we're moving now into what appears to be what are called conditional probability problems. And there's some formulas here. Did you get a probability like A given B?
Is for what?
Did you get some formulas like this at some point in class?
No, I'm sorry. I'm just looking. Yeah, I think on the first page of like what I sent you. Sorry, I printed it out. I'm looking at it. There are some things.
Okay.
Like it says like complementary events, the additive law, conditional probability.
Yeah, so this one's the conditional probability. It's not very helpful the way it's written. Like this is not helpful, but let's turn it into the words here. So here's what we want. We want the probability that it's a rainy day given that it's cloudy. So probability rainy given that it's cloudy. That's what we're trying to figure out. So it's better to map like these letters to yours. So we want the probability that it's rainy and cloudy over the probability that it's cloudy. Okay, and so you do need to know the formula, but you immediately want to translate it to the things that it says here. See the given is that it's cloudy. That's the second part. So the given, it goes after the vertical bar.
Oh, okay, yeah. It's like the given that, or what are the other words? It's like, is it if? Is that another word?
Yeah, assuming, or like it's a baseline thing.
Okay. Sorry.
So you could say something like if. Sorry, do you need to?
Oh, I was just, I might make some noise. My pen just died, so I have to grab one on my back. But I'm good now.
So if like you say, if you're a man, what's the probability that you play basketball? That's the other way that it can be written. The if, the given that, the assumption that, those are that goes after there. The thing that you're trying to find the probability of goes first. Now your lesson notes here say objective and the condition, which, I mean, it's true, but it's not helpful.
Yeah, I found those words yeah, kind of confusing.
It's like formal versus informal. It's
Okay.
like, let's, hey, may I take you on a date? Or hey, let's go grab food. It's you gotta, not you specifically, but just a, we have,
Yeah.
we know language because we're native speakers. But even I don't like the formality of this. It doesn't help for learning. So the other thing here is that they only give you two numbers in the problem. So there's only a couple of things you could do. You can either add, subtract, multiply, or divide. But, if you recognize it's conditional, you will say, oh, well, probably if both is 0.1, the probability that it's cloudy is 0.3. And there's your answer. It's 1/3 or 0.33. So that's another kind of aside, is like, you don't have to get super complicated with things because you generally only have a couple of options when it comes to what to do. All right, so let's look at this classic problem here with marbles or socks. I threw a sock question up on my social media account the other day. It's I guess nowadays there's a trend to wear socks that are mismatched.
Yeah, I've always noticed like girls that do that when they do like the smaller socks that you can't see, like
Yes.
like that. But yeah, I don't know what is that what people are doing now. People are just like wearing orange and purple socks.
And I think it's more just they don't want to sort their laundry.
Are you the guy though? Do you do that? Do you torture all your followers with like hard math questions?
I try to so do them by skill level. So this one was just a probability success for, I just pick a class each day that I do one and post a question.
Okay.
Like that yesterday's for algebra one was just about equations of a line. I mean, but there's obviously calculus 1, 2, and 3 questions that I'll do that are way more difficult. But the idea is to give students something that they can do, so that because I think what I found is people want to do it, they don't necessarily post the answer. But anyway.
Yeah.
So here you go. We got a box containing 25 marbles. Sometimes it's good just to add them up: 4 + 2 + 5 + 6 + 8, and see if it actually does add up to 25, and it does. Okay. Now there's two things that you have to, the first thing you have to know is whether there's replacement or no replacement. Oh. Sorry, my screen just kind of
Yeah. Okay, cool.
there,
Okay.
we're back. Replacement or no replacement. And the words are sort of self-defined, but I'll just say it anyway. So the idea is if you're doing replacement, that means that you pull a marble out and it stays out, or it goes back in. No replacement is you pull it out and it stays out. All right. And that's what they're saying here. They're saying once a marble is drawn and is not returned to the box, that means
no
that there's
replacement.
no replacement. Okay.
Okay.
And that's important. Okay. And we want to find the probability that the first marble is yellow, second is red, and it should say and here. This is very important. And so another thing with and is you're generally multiplying. So you have first event times the second event times the third event. So the first event is yellow. So how many yellow are in here?
4.
Out of 25. Okay, now this is important here. You have to assume you actually pulled out a yellow. And that's maybe kind of obvious, but just you pulled out a yellow. Okay, so and if you need to, you can just, okay, let me go, let me just change this to now there are 3 yellow, if that helps. All right. So now the second one is red. How many red are there? Well, there's 2 red. 2 red. And since you assume you pulled out a yellow, how many marbles are left over?
24.
24. Okay. And then you assume that the third is orange. There are 6 orange, but there's 23 because you pulled out 1 for the red. And there's your value. Okay. And again, kind of same thing applies here. You need to get a number between 0 and 1. So if you're using a calculator, just be careful with parentheses and things like that. You should not get a number bigger than 1 ever on this. All right. And this is pretty common. Numbers go down 25, 24, 23, and so on. So let's just do one kind of related problem, the one that you often see. What's the probability that they're all yellow? Okay, rather than this, because you're pulling out 3, but they're all yellow. Okay, so there are 4 yellows to start. You pull 1 out, 3 yellows, pull 1 out, 2 yellows, like this. And that's when the numbers on both the top and the bottom descend.
Sorry, just is the third number, is it 22 or is it supposed to be 23?
23, sorry.
Okay. I was making sure.
Sorry, yeah.
Okay. And then it's just the same way, like as far as the way you find it, you just multiply this together the same way.
Multiply the top, multiply the bottom, divide, you get a pretty small number. All right, next question here is kind of like a password type question, or a gate or a door question. So a man wishes to open his door in the dark. He has 5 keys and try them in his door at random. That is, it is possible he tries the same key twice in succession. Only one of his keys will open the door. What is the probability that the first key to fit the door is the third key he tries? Okay. Okay. So this is like a pass fail situation. It used to be when you called customer service or even like a friend, sometimes you get a busy signal. It's rare today because they just put you through to anything. But you used to say, okay, like fail. Well, here's some outcomes possibly versus like and I prefer like connecting, but we'll call it pass. You could immediately pass, okay, get right through, or you could fail and then pass, fail, pass, pass, fail, pass, pass, pass. I'm sorry. This is not correct. You could fail, fail, pass, fail, 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 pass, fail, 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 pass. Okay, and this kind of works in this example here. So if you pass, like if you open up the door first, you're very happy, but you could also fail and then pass. Fail, you could, wrong key, correct key, wrong, correct, and so on. So you have to sort of like, and this is sort of oddly written. It's a good question, but it's oddly written because what we want is the probability that the first key to fit the door is the third key he tries. So basically we want this scenario right here.
Okay.
Okay. So you have to know, you have to figure out in this problem is what is the probability of failing and what is the probability of success? Actually, that was probably a better word. So success, I think, is easier. There's 1 out of 5 keys that works. Failure is 1 minus success, or 1 minus 1/5 or 4/5. But fail and success have to add up to 1.
So I'm writing it down. And then they have to add up to 1.
Yeah, failure and success, because they're actually, well, we didn't even talk about this. They're mutually exclusive. Like you either fail or you pass. There is no both. You can't, the one I guess I like because is pregnant. You're either pregnant or not pregnant. There's no sort of lights either on or off, that kind of thing. All right. So now the scenario here, which is oddly written, but it says, what is probably the first key to fit the door is the third key he tries. So that means you went failure, success. So it's 4/5 times 4/5 times 1/5.
And then what do you do from there?
That's it. You multiply the numbers. Like when you have these compound events, failure and pass, or failure and success, you always multiply. And just like in the previous problem, you would multiply.
So I'm not doing it wrong. Are you saying like on them, it's like 5 times 5 times 5?
Well, your numerator is 4 times 4 times 1, 16 over 125.
Okay. Just making sure.
Yes. And the previous ones we didn't multiply out, but you're really just going
the same exact way, right?
Yeah, and you're going to your calculator at this point. I mean, this one's you could probably do kind of like but it's fine. Like they should accept both. Like you're supposed to use a calculator in this class. It's not like other classes where it's up for debate.
So yeah, and I think we'll have Excel where you can throw the stuff into like cells and come up with the answer.
Yes, you can do it right in Excel as well.
Okay, that makes sense. Definitely getting a better handle on.
Good.
Can we skip ahead to one?
Yes. I was going to actually suggest we not do this next one because it's Bayes' theorem gets more complicated.
And then I think it's just the next page. Yeah, page like page 4 for me. But assignment number 3.
Yes.
And then number 2 of that.
Yes. Okay. Yeah, this is actually good because this was good here. So all right, so let me snip it in here. A small factory has 3 machines, A, B, and C, that produces defective and non-defective parts. Okay. So you have to draw what's called a tree diagram. So you have A, B, and C. And what I like to do, and I think this is very important, is actually to put the probabilities along the paths, not at the end of the paths. 0.2. And so because there's only 3 machines, but they only give you 2 of them, you have to find the other one. So you know that 0.4 plus 0.2 plus B equals 1 because they have to all add up to 1 because probabilities all add up to 1. So B is 0.4. But they're not giving that to you.
Okay. Yeah.
Okay. And then this is a good question, but it wouldn't be the first one I would give you if you were learning this from scratch. But then each of these, they have both a defective and not. And you want to be consistent with your patterning here. So you want to you want to either say, okay, not defective, defective, not defective, defective. You want to choose the same order each time. And it doesn't matter. You could go defective end. It really doesn't matter, but be consistent. Consistency is key. All right. So now if you go to triple I, man, this person made this way too complicated. I'm sorry. So okay. Your instructor didn't do any. So normally they say like letter V, where it says 75% of the part made on machine A are non-defective. So that means that's 0.75 there and 0.25 there. They normally give you the value of each of these, but the instructor was not that kind here. Okay, so we'll get to that in a moment. So that's letter V. Letter V gets us those. We need to go back to IV, where it says 20% of the defective parts were made on machine C. So what that is saying is that I don't want to say this. Yeah. So they're saying that 0.2 were defective here, and that means that 0.8 is there. Because each sort of branch has to add up to 1 on its own. While up here there was a triple branch. Then the triple I, this is I'm sorry, this one's way more complicated than it needs to be. It says 15% of all parts are defective. So how are they? What does that mean? It means if you go down the defective, so if you go A to D, that's 0.4 times 0.25 plus, and so we don't actually know this one, B, 0.4 times X, because those are defective, plus 0.2 C, 0.2 defective. If we go down these branches, and when you go down a branch, you multiply, they're saying that is 0.15.
Okay.
And I'm sorry, normally they just give you the values and then you use something else, but they're really reaching here for this one. So solving this equation, you obviously get a calculator here. You got to do 0.25 times 0.4 times 0.25, which I believe is 0.1. I think 4%. No, 1% is might be 0.01. Let me grab my calculator. I don't want to make a mistake on this. 0.4 times 0.25, yeah, 0.1 plus 0.4x plus 0.04 equals 0.15. So 0.14, so we have 0.4x equals 0.01. 0.01 divided by 0.04 is 2.5%. Wow. Okay. So this is 0.025 and this is 0.975. Okay. And the reason we do all this is you generally need to know every number in this thing to be able to answer any of the questions. That's why it's so important that you be able to fill it out correctly the first time. Okay, so why do we do that? It's like, so now we can answer some questions. So the first question is, what is the probability that the part was produced? I'll grab this one, on machine A or machine B. So sometimes you don't have to go through the entire tree, but let me grab this question. Okay, so A or B, that means I either went down A or I went down B, and that's 0.4 plus 0.4. That's not too bad. 0.8. Oh, so these are so confusing. These are done in such a bad order. Let's do C next. So C says, what is the probability that a part made on machine B is defective? So what that means is you're starting on this path B and you're going down to the defective route. And whenever you go down a route, a path, you multiply. So that's the 0.4 times the 0.025. And it's okay if this is, super unclear, but that is like, that's the types of questions you're going to be asked here, is to
Okay.
either count or go down a path. Okay, now we'll go back to B. Okay, so what is the probability that the part was either produced on machine A or is defective? Okay, so let's look at what that means. So machine A, we know machine A is 0.4,
Mhm.
but we also want the other ones that are defective. But we don't want to double count. So we don't want to go down A to defective because we already have that here. So we need to go down B in defective, C in defective.
Okay.
You don't double count here. So it's the 0.4 plus, and then we got to go down that path here, the B 0.4, 0.025. And you're always multiplying. Plus, when you go down C, 0.2, 0.2 for defective. That's the D. So 0.2 times 0.2. So 0.4 plus 0.01 plus 0.04 looks like it's 0.445.
Okay.
Okay, I think we should move on to another question. I don't know. I mean, we can keep going, but I mean, my concern is this is really unclear.
Yeah.
Let me actually draw. Let me see if I can go back to 9 and draw the diagram, because I think that'll help from the previous problem. It's a little bit simpler to start out with. Okay, so one of the things that you can read this year, there's a detection of a disease problem. You have to first decide, well, what's my first branch? And I think in the previous problem it's kind of obvious. Okay, it's either A, B, or C, and then you decide whether it's pass fail kind of thing. But here you first have to decide whether the person detect it or not detect it, or whether they have hepatitis or don't have hepatitis. Is that kind of clear? Like, so you either have to say, okay, hepatitis, not. Okay, so 80% of the people, sorry, so of the people without hepatitis, 5% are erroneously diagnosed. Okay, 1% have hepatitis. Sorry, so hepatitis is 0.01, and this is 0.99. Okay, so then of the people with hepatitis, so that's now down this branch, you have disease or not. So of the people with hepatitis, so that's already here, and that's kind of how you answer this, whether it's hepatitis or not, or the test works or not. Usually the testing goes down at the end of this. Of people with hepatitis, 80% of the blood tests detect the disease. So that means 0.8 detect the disease, but 0.2 do not. But if you don't have it, you can still have the disease, or the test can still predict that you have the disease. So that's where this next sentence comes in. Of people without hepatitis, going down the other way, they are 5% are erroneously diagnosed as having disease. So they don't have it, but the test says that they do. And that means that the other 95% say that they don't.
Okay.
And if that, I'm putting this up here because you may want to review this later on in your notes or the YouTube and just see if hey, if you get this. But the most important thing is actually be able to draw the picture, the tree diagram here. And then you can answer the questions like, what's the probability? Like, here's the most common question you've asked: what's the probability that you actually have the disease? Because there's people who have it and they get diagnosed with it, and then there's people who say they don't have it, and then but they actually They are diagnosed with it. Or I guess that would be, what's the probability that you're diagnosed with the diseased? And that's the 0.01 times the 0.8 plus the 0.99 times the 0.05. And just as an aside, this does happen, but not to this degree in the real medical field. But you hear about it every once in a while. You know, someone didn't realize that they, you know, had a disease. You know, they'd been tested, and so on. But so the probabilities aren't this large.
Yeah.
In any way. And all this is what's called Bayes' theorem. So if you go to class again, I would just ask for more help on Bayes' theorem. It's usually the thing that most students really struggle with.
Okay.
And that way you can get some extra help on it. We obviously didn't get through everything on this document today, but you know, maybe another lesson or two we can get through everything.
Yeah, I'll let you know. I'll probably be pretty weekly.
Sounds good. Thank you so much.
But yeah, I really appreciate it.
I'll send you the notes here shortly, and I'll link to the YouTube when it's uploaded.
All right. I really
Thank
appreciate it.
Okay.
Have a good rest of your day. Good weekend.
You too.